Okay, this is 5.3 polynomial functions. This is a long section. Our objectives are we're going to evaluate a polynomial function and we're going to identify general shapes of graphs of polynomial functions. And you'll see we have, if you open your 5.3 video overview, there's a lot of vocabulary. Most of these down here are just determining by degree. So let's get started and let's start on page 322. So they're talking about a polynomial in one variable. So if you look at the general form, it's going to be a subscript n x to the n plus a subscript n minus 1 x to the n minus 1. Okay, and so on and so on and so on until you get to the very end where you have a of 0. And a is going to be real numbers, and n is going to be a non-negative integer. That's what it has to be. Can't be negative to be a polynomial. All right. We also said a of n cannot equal 0. Okay. So when we put them in degree order, and that's what we're talking about. We're talking about the degrees. This is a general form. So, for instance, let's just go straight into an example. So we look at ax to the fifth minus 4x cubed plus 2x squared minus x minus 3. We're saying we have one variable x, and they're in degree order, 5, 3, 2, 1, and then your constant. Right? So we take this polynomial and we find the degree of each one. This term has a degree of 5 because a constant has a degree of 0 plus 5. This one has 3. This one has a degree of 2, 1, and 0. Constants always have a degree of 0. So these are the degrees of each term. So you put them in order by degree from greatest to least. The first term, which is the greatest degree, its coefficient, which is 8, is called the lead coefficient. So that's one of your vocabulary words. And you need to know leading coefficient is the coefficient of the first term of a polynomial in standard form. Standard form is it's in degree order from greatest to least. Now we have a constant, 12. This is called a constant. It's a type of polynomial. Its degree is 0 and its lead coefficient is going to be 12. If I have 4x minus 9, this is called a linear because it has a degree of 1. Linear means 1. And its lead coefficient is going to be 4 because that's a degree of 1 and 0. Now let's look at this one. 5x squared minus 6x minus 9. This has a highest degree of 2, this polynomial. So it's called a quadratic polynomial, and its lead coefficient is 5. If we look at 8x cubed plus 12x squared minus 3x plus 1, its degree is 3 because that's the highest degree of all the terms, and the lead coefficient is 8. So in general, the degree is going to be the highest degree of the polynomial, and its lead coefficient is going to be its variable, its coefficient. All right, so let's look at an example when we've already done A. It says determine if they are polynomial in one variable. If it is, what is the degree and the lead coefficient? If it's not, explain why not. So we have 12x squared minus 3xy plus 8x. This is not because I don't have one variable. I have two variables. I have an x and y, so it's not a polynomial in one variable. Let's look at the next one. 3x to the fourth plus 6x cubed minus 4x to the eighth plus 2x. So they're not in degree order. If I rearrange them, it's going to be 4x to the eighth plus 3x to the fourth plus 6x cubed plus 2x. Now they're in degree order. So it has a degree of 8, and its lead coefficient is negative 4. So don't assume that it's in degree order and that this is always the degree of the polynomial. You have to put them in degree order, and the highest is the degree. All right? So let's move on to our next vocabulary. A polynomial function, it's just a fancy word, that's all. Polynomial and a function just says it's a continuous function that can be described by a polynomial equation in one variable. For example, f of x is equal to 3x cubed minus 4x plus 6. It's one variable, it's a polynomial function, and it's called a cubic because the highest degree is 3. All right, so the simplest form of a polynomial function is f of x equal ax to the b, where a and b are non-zero. Real numbers are called power functions. If you know an element in the domain of any polynomial, that means one x coordinate, you can find the corresponding value in the range or the corresponding y value. So let's look at real world example number 2. They refer to the beginning of the book and says, find the volume of air in the lungs 2 seconds into the respiratory cycle. So basically they want us to find f of 2. And in the beginning they give us the function is negative 0.037 t squared plus 0.15 cubed t squared plus 0.173 t. So all we're doing is we're replacing t with 2. If we put that in there, we get 0.658 liters is the volume of air in your respiratory cycle. All right, so substituting one variable is easy. Let's look at function values of variables. So on example 3, they want you to find f of 3c minus 4 minus 5 times f of c. And they tell you f of x equals x squared plus 2x minus 3. So this right here is going to be our function. So basically we're replacing, just like we did earlier when we did f of 2, we put that into the function. We're going to put this into the function of x. So we're going to say f of 3c minus 4 equals 3c minus 4. We're replacing it for x squared plus 2 times 3c minus 4 minus 3. So all we did is we put this value, just like we did here, into our function equation for x. Now we're going to FOIL this. They did it for us, so I'm not going to do this all out. You're going to do this times this. You can't use the power rule because I have more than one term. And then you're going to distribute this, and then you're going to combine all the like terms. If you want to see how to do it, it's on page 323. The book does it for us, so it's basically 9c squared minus 18c plus 5, and that's what we get. Now we need to do f of c. So f of c equals, we put c into here, so we have c squared plus 2c minus 3. But we need to do 5 times it. So now I need to do 5 times f of, I'm going to put a little multiplication, times f of c. Okay, so I'm going to multiply that by 5. So I get 5c squared plus 10c minus 15. So now I have this and this, which is this and this. So now I simply take this, which is, another color here, 9c squared minus 18c plus 5 minus everything here. So that's going to be, I'm going to write down here, 5, I have to distribute that negative, minus 10c plus 15. And then all I have to do is combine like terms. So I get 14c squared, these two are like, so minus 28c. Oh, this is a minus 5. I missed that. So this is actually 4, not 14. And I already changed the signs on all these. I just realized that went right here. All right, so it's 4c squared minus 28c plus 20. And there's your answer. So don't let, because it's more than one term or it's another variable, scare you. Okay, here's this next section. Turn to page 324. Graphs of polynomial functions. And if you look at the top of page 324, they're going to give you the general forms A constant, so they're saying the general shapes of the graphs of several polynomial functions shows the maximum number of times the graph of each function intersects the x-axis or crosses the x-axis. This is the same number as the degree of the polynomial. So the first one's a constant function, which is y equals some number. That has a degree of 0, so if you look at it, does it cross the x-axis? No. So its degree is 0 and it crosses 0 times. The next one's a linear equation, which is, we know y equals mx plus b, has a degree of 1. It crosses the x-axis once. The next one's a quadratic function, which has, what, x squared, so it has a degree of 2, and you notice it crosses twice. You have a cubic function, which is a degree of 3, crosses 3 times. The quartic function, which has a degree of 4, crosses 4 times. And then the quintic function, which is a degree of 5, crosses 5 times. Now, this is important. Now, you're saying, but sometimes a quadratic equation doesn't cross. It'd be 0 if it has a degree of 2. We'll talk about that later. For right now, we're going to assume that it crosses at the same number of times as the degree. That is a question for later. All right, so now we're going to talk about the end behavior. What is the end behavior? So if I have a graph, for instance, quadratic, the end behaviors are the two arrows. This is an end behavior, and this is an end behavior. So we're saying, what happens to the range or the y values as x approaches positive infinity and as x approaches negative infinity? So as x is approaching positive infinity, this is x, it's going this way. What's happening to my y? It's approaching negative infinity. And if I go this way, as my x approaches negative infinity, goes in this direction, what happens to my y, my range? It's also approaching negative infinity. So these are called the end behaviors. And if you look at the bottom of 324, there's a box that kind of recaps. So let's look at this. Quadratic, they give you the function this. The end behavior is what's happening. As x is approaching positive infinity, y is approaching positive infinity, right? So f of x is approaching positive infinity. And as x approaches negative infinity, f of x, which is a fancy word for y, is approaching positive infinity as well. So the domain is all real numbers. The range is going to be all real numbers or y greater or equal than the minimum. And you see that this is a quadratic. It's an even, right? It's going to be an x squared as the parent function. It has a degree of 2, so that means that's an even number. The lead coefficient is positive, so it opens up. So that means the end behavior, if the lead coefficient, which is 1, is positive, then the end behaviors are going to be positive, and they're going to be the same because they're even. If A was negative, it's going to open down. If A is negative, the lead, which is a lead coefficient, the end behaviors are going to approach negative infinity, and they're going to go in the same direction because it's an even. Now let's look at one with an odd. So let's take this for instance. This, you don't know it yet, but its function is x cubed. So A is positive, which means this always refers to the end, to the right side, as x approaches positive infinity. It's positive, so its end behavior is going to go up. Because it's an odd, the beginning end behavior is going to be opposite. So if this is going up, this has to go down. All right, now what if this was negative? Then our function is going to look like this. So if this was negative right here, because this is positive for that one, if f of x equal negative x cubed, if our lead coefficient's negative, so our end behavior is going to go approach negative infinity to the right. And because it's odd, this one has to go up. So as x approaches negative infinity, f of x approaches positive infinity. As x approaches positive infinity, see, x is going this way. That's what it means by approaching, as x gets bigger. Then f of x, or the y, or the range, that's why it approaches negative infinity, and they approach opposite. All right, so the number of real zeros of a polynomial function can be determined by examining its graph. Recall the real zeros occur at the x-intercept, so the number of times a graph crosses the x-axis is the number of real zeros. So odd degree functions always have an odd number of real zeros. Even always have an even number of real zeros, or no real zeros at all. So let's look at page 325. You see that this function does this. Does it cross? It's going to have an even degree because the end behaviors go in the same direction. So it's going to have an even degree as its degree for the polynomial. But it never crosses the x-axis, so it crosses 0 times. Look at the next one. It does something like this. Okay, so we know it's going to be even because the end behaviors are in the same direction. We know it's going to be negative because they're both going down, the lead coefficient. And we know it crosses 1, 2, 3, 4 times, so it has 4 zeros. So that goes with the even degree, correct? Look at the odd degree polynomials. You have one that does, okay, so we know it ends in going up, so the lead coefficient is going to be positive. We know it's going to be an odd degree because they go in opposite directions, and we have 1, 2, 3 zeros, which indicates you have a degree of 3. Look at the other one, the other example. They give you, it does this, all right? So the end behavior is negative, so the lead coefficient sign is going to be negative. We know that it's going to be odd because they go in opposite directions. It crosses 1 time. Is 1 odd? Yes, so it has a degree of 1. Actually, it has another degree, but we'll learn more about that later. So let's look at example 4. It says, for each graph, describe the end behavior, determine whether it represents an odd or even degree polynomial function, and state the number of real zeros. So A, they both are going in the same direction, the end behavior, so they're even. And as f of x, as x approaches positive infinity, f of x approaches negative infinity, which tells us what? It tells us that the lead coefficient is going to be negative. It's going to have an even degree, and it crosses 2 times, so it has 2 real zeros. That's all they want us to answer. And they want us to describe the end behavior as x approaches positive infinity and negative infinity, f of x approaches negative infinity for both cases. In B, they go in opposite directions. So as f of x approaches positive infinity, as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches positive infinity. They both, it's going to have an odd degree. We describe the behavior degree. Its lead coefficient is going to be negative because the end behavior goes down. And it's got 1, 2, 3, 4, 5 real zeros, which is an odd number, which goes with our odd degree. All right. So now you need to do problems number 2, 6, and 15, and we'll see you in class.